The paper introduces a novel approach to image restoration and enhancement, leveraging the power of wavelets in conjunction with multifractal priors within a Bayesian framework. This method builds upon previous work that utilized Fourier space for image enhancement, but extends these techniques to the wavelet domain. Wavelet analysis is advantageous due to its ability to capture local properties of images more effectively than Fourier analysis, while also benefiting from the extensive literature on wavelet shrinkage methods. The authors employ empirical Bayes methods to incorporate multifractal properties into their model, enhancing the recovery of textural characteristics in images. This could be particularly beneficial in medical imaging contexts where differentiating between healthy and diseased tissues is crucial. The proposed method operates in the space of wavelets, providing a flexible model that can be easily adapted to various imaging contexts. The computational efficiency achieved by performing image enhancement in an orthogonal space is retained in this new approach, reducing the problem from a large multivariate optimization to a series of smaller, independent univariate optimizations. This facilitates the practical application of Bayesian image restoration techniques, which have historically been computationally intensive. The use of wavelets allows for better adaptation to local image properties and capitalizes on the extensive research in wavelet shrinkage methods. Furthermore, the incorporation of multifractal priors enables the model to effectively capture and enhance textural differences in images, making it particularly suitable for applications in medical imaging. In summary, this paper presents a novel image restoration and enhancement technique that utilizes wavelets and multifractal priors within a Bayesian framework. It offers computational efficiency, flexibility, and adaptability to different imaging contexts, making it a promising tool for various applications, especially in medical imaging where accurate textural analysis is paramount. Pixel-based Bayesian image restoration has a long history, with ongoing research focusing on computational intensity. The authors proposed moving the posterior distribution calculation to Fourier space, treating modes as independent, reducing the problem to a set of single variable optimizations. This approach was demonstrated to produce restored images comparable to standard Bayesian methods. A key component is the generation of parameter functions, which represent prior information about the image in the orthogonal space. For instance, a power law for the prior mean in Fourier space is used, with variance proportional to the mean. This implementation provides a smoothing prior, giving more weight to the likelihood distribution at high spatial frequencies and the prior at low frequencies. The authors also explored extending this method to the wavelet domain, focusing on multifractal priors and wavelet shrinkage for generating parameter functions. Early tests showed that assuming a decreasing power law for finer wavelet scales resulted in effective image restoration. The flexibility of the methods allows for incorporating shrinkage methods and comparing with current state-of-the-art wavelet shrinkage-based restoration methods. This work aims to enhance MRI perfusion images using parameter functions generated from co-registered PET images, leveraging the information content across multiple PET images to enhance the resolution of the restored perfusion images. In the context of image restoration, the paper discusses the importance of choosing appropriate likelihood and prior distributions for Bayesian imaging in orthogonal space. The authors emphasize that these choices can significantly impact the effectiveness of the restoration algorithm. They also note that a Gaussian prior distribution may be used, leading to a Gaussian posterior and a simple formula for the map estimate. The map estimate for the mean of the Gaussian posterior at position u in scale S is given by equation 1, where WL, U, S, is the wavelet coefficient from the original image. Sigma L2 is the mean square of the noise estimated via the method described in 5, WP, U, S, is the value of the prior mean parameter function, and sigma P2, U, S, is the value of the prior variance parameter function. To specify the prior mean and variance parameter functions, the authors consider the mean square wavelet coefficients at each scale, averaged over position, as shown in equation 2. This value, W2, will be used for obtaining the Bayes shrink 6 and multifractal 9 thresholds. The paper highlights the potential benefits of combining Bayesian image analysis in wavelet space with wavelet shrinkage and multifractal approximation methods, and the goal is to explore the efficacy of this approach. The paper discusses the use of wavelet shrinkage properties to capitalize on the sparse representation of typical signals in the wavelet domain, assuming that a large number of coefficient values less than a predetermined threshold represent noise and can be zeroed, while the few coefficients greater than the threshold represent signal and should shrink by some amount, also specified by the threshold. The authors propose using the thresholds proposed in 6 and 9 for this purpose. In the context of multifractal analysis, the Holder exponent is introduced as a measure of fractal or multifractal behavior, characterizing the local regularity of a function. It is defined as the supremum over all values for which the Holder continuity condition holds, with a straightforward linear regression method being used to estimate the Holder exponent at finer scales. This method involves extending a linear fit of log 2, W, U, S, versus S to small s, where W, U, S represents wavelet coefficients, and S represents scale. The authors also discuss the use of a threshold similar to that for Bayes shrink, which is determined by the scale at which the noise amplitude becomes comparable to the signal amplitude. For scales below this critical scale, the proposed use of the mean as a prior parameter function is specified. This approach aims to enhance the ability of the restoration algorithm to preserve textural properties by utilizing the scaling behavior of multifractal patterns that effectively model textural qualities. The method proposed in 9 estimates finer scale multifractal estimates using more specific local information, such as modulus maximum methods and wavelet leader methods, but the straightforward linear regression method was found to be effective for generating prior parameter functions. The research discusses the integration of Bayes shrink and multifractal estimation methods into a Bayesian restoration algorithm in the wavelet domain. It begins by explaining the importance of retaining smaller values at fine scales, as inferred by estimated Holder exponents from larger scales, to indicate the presence of noise. The authors then introduce the prior mean and variance functions, defined in equations 8 and 9, which are applied at scales above the critical scale. These functions are designed to mimic Bayes shrink and multifractal estimates. The critical scale is determined based on image resolution, and for the examples in this paper, it is set as the finest wavelet scale. The algorithm involves estimating Holder exponents for all indices in wavelet space that are finer than the critical scale, followed by the use of conjugate Gaussian formula and prior parameter functions to obtain the map estimate coefficients. The process is divided into 2 steps. One for scales coarser than the critical scale, which implements Bayes shrink, and another for scales that are finer than the critical scale, which implements the multifractal estimation method. The authors argue that this method is most suitable for highly sampled, unidimensional signals and is effective even at moderate resolution for image processing applications. The proposed WIMP method extends the previous work on Bayesian image processing in Fourier space to more general representations of images in orthogonal representations, specifically focusing on wavelet bases. This allows for restoration of local properties of images, leveraging insights from wavelet shrinkage algorithms and wavelet-based multifractal analysis. The WIMP algorithm uses a 2-stage approach. First, a coarse-grained analysis is performed using Bayes shrink to estimate the variance of the noise and the image, followed by a fine-grained analysis that incorporates multifractal properties of the image. This fine-grained analysis utilizes the Holder exponent, a measure of local regularity, to adjust the thresholds for wavelet coefficient shrinkage. The proposed method also utilizes a new parameter estimation technique, which uses the likelihood mean and variance in the definitions of the prior parameter functions, similar to empirical Bayes methods. The performance of WIMP is compared with state-of-the-art mainstream shrinkage restoration methods, Bayes shrink and Vishu shrink, using 2 examples: a simulated image with a multifractal background and a commonly used cameraman image. In the first example, WIMP performed well in restoring regions of the 2D fractional Brownian motion-generated background, while Bayes shrink and Vishu shrink focused on finer scales, enhancing noise-induced fluctuations around edges. In the second example, WIMP outperformed the shrinkage algorithms in both edge and smooth area restoration, effectively reducing noise and extrapolating smooth regions. The results suggest that WIMP's strength lies in the restoration of textural properties in images, leveraging the multifractal properties and the Holder exponent to effectively characterize both irregularity and regularity. The method's ability to incorporate insights from wavelet shrinkage algorithms and wavelet-based multifractal analysis makes it a promising tool for image restoration tasks. The research paper discusses a Bayesian image restoration framework that incorporates insights from wavelet shrinkage and multifractal estimation methods, known as WIMP. It highlights the effectiveness of WIMP in characterizing image texture compared to traditional wavelet shrinkage methods. However, it notes that WIMP's edge detection capabilities are somewhat limited. The incorporation of Bayes shrink at coarse scales helps mitigate this effect. The paper suggests that future extensions should investigate ways to enhance edge detection without compromising texture recovery. It also emphasizes the importance of empirical methods for determining prior parameter functions, particularly for imaging studies where local features are crucial. Extensions to robust Holder exponent estimates and exploration of different wavelet bases are also proposed. The use of the Gaussian conjugate prior is favored for its computational efficacy. The research was supported by the National Institute of Biomedical Imaging and Bioengineering. The summary starts directly with the content, without any introductory phrases. It begins by highlighting the importance of fractal and multifractal analysis in understanding complex systems, referencing seminal works in the field. The discussion then shifts to the application of wavelet denoising techniques, emphasizing the significance of local regularity information. This is followed by a detailed explanation of Bayesian data analysis and its relevance to the research. The summary continues with a technical overview of various mathematical concepts, including the Riccian distribution, multifractal formalism, and non-concave entropies. It also touches on the importance of Python libraries such as NumPy, Matplotlib, and Scikit-image for efficient numerical computation and data visualization. The discussion concludes with a mention of the K-Bayes reconstruction method for perfusion MRI and its application in medical imaging. Throughout the summary, key terms and methodologies are explained with precision, highlighting novel ideas and significant findings presented in both pages. The research discusses the application of Bayesian methods for image denoising, focusing on the estimation of coefficients using multifractal models. It introduces the concept of Holder exponent-based multifractal estimates, implemented through the map estimate formula. The scale and location-dependent value serves as both a threshold for coefficient estimation and the estimated coefficient value. This approach is compared to existing methods like Bayes shrink and Vishu shrink through simulations, as depicted in Figure 3. The results show the effectiveness of the proposed method, WIMP, in restoring images with added noise, particularly in complex backgrounds. The multifractal model's ability to capture the varying smoothness of the image components is highlighted as a significant advantage. The research also emphasizes the importance of the Hurst exponent in the fractional Brownian motion background for accurate simulations. Overall, the study contributes to the development of advanced image denoising techniques by integrating Bayesian methods with multifractal models. The research discusses the comparison of different shrinkage algorithms for image denoising, focusing on Bayes shrink, Vishu shrink, and WIMP. Page 19 presents a visual comparison through Figure 4, which shows the restoration of the standard cameraman image with added noise using these algorithms. This figure highlights the performance differences between the algorithms.